Hello, this is Project 1, Part 2, the Fluent 2D flow simulation of airflow over a flat plate. Already got answers loaded up. Start up with Fluent and go straight into geometry. It's pretty... Geometry, this one's pretty simple, you'll see here in a second. You want to go to that XY axis, go to Sketch. First of all, don't do that. Make sure you're in the right units up here. Makes things a little easier. In this case, since our length is 100 centimeters, I'm just going to put it into centimeters. Put that coincident, zoom out a little bit so you could just see what you're working with. Amazing. Now, once you make your box, go general. Give your front and your back a dimension. Let's make this 50. Height's not that important. Just don't make it ridiculously small, so you can actually see your boundary layer develop. But length, 100 centimeters, whatever. Then you're going to go on to concepts, surfaces from sketch. You can go to your XY plane, select your sketch, apply, generate, and look at that. You have a 100 centimeter long box that is 50 centimeters tall. That's all we need to do in geometry. Close out of that app. Open the mesh app. Let's give you the first part of all of it. All right. Put her in the Z plane as usual. And then you can, if you wanted to, you could generate your mesh, but you're going to know that it looks... Ugh, that's not good. That's not going to do because we're going to need to be able to get a good boundary layer in the bottom. And if it's this big, you're not getting anything. Get back to that in a second. Let's start with our model. Click here on the edge tool or just be really accurate. And let's name all of our surfaces. Always start with the inlet so you know what you're working with. And you start with your outlet, so ANSYS knows where the inlet and outlet is. Here, name it flat plate. And I'll just throw bottom in case, I don't know, I forget. Top, we're going to name something different. Symmetry. You can name this top, but it's very important in the next step that you have to go through on the boundary conditions, and you have to switch the top plate into symmetry. Or just name it symmetry now, and it'll be simple. Because this is a free-flowing area. There is no top to the box. That would be part 1. Moving on to the mesh, we are going to insert our first sizing. Select the front and the back. Control left click them both as our geometry. Switch this to number of divisions. See how 100 looks. 100 looks pretty good. Maybe actually, let's go to stick to 100. But what we're going to do is get rid of capture curvature. Growth rate's fine. Turn it to hard behavior. And we're going to enable a bias. Bias factor, let's do 60. I'm going to reverse the bias of this edge, and then you could see that when this is made, you're going to have very few at the top because we don't honestly care too much about what's going on at the top. That's whatever. This is like free stream, whatever here. What we really care about is our boundary layer down here. So we want as many meshes as possible down there. We'll generate that so you can see what it looks like. It kind of looks a little yucky right now, but you can see how thin the mesh gets at the bottom. That's good. That's what we want. We're going to do the same thing for the top and the bottom, but without the what's it called? Bias. So just do number of divisions. Since this is bigger, we'll just do twice as many. 200 looks pretty good. You can honestly go to what your heart feels like. Maybe not too many because ANSYS might get a little upset. I think 200, 150 is probably your minimum. But I'm just going to turn off all this. Hard behavior. Then we'll update again so you guys can see how it's coming along. Ugh. Look at that. It's not quite there yet. Gotta do one last thing, if I'm not mistaken. We need to do face meshing. Yes. Select your geometry, quadrilaterals, mapped mesh, not suppressed, extreme boundary. Nope, nope, nope. It should be fine as that. Now, if we generate our mesh, look at that. Beautiful, isn't it? Here we can see you have this really accurate boundary layer down here. But up here, not so accurate because we don't really care up here. And if it's too fine up here, you're just wasting processing power. So you can make a more accurate model and save some of the processing power for what you really care about, which is what's down below. So once you have all your services named, you've got your mesh, you are good to generate it and then exit. If you named your surfaces, always got to update it out here too. No harm. Just make sure you're always up to date on what your model's doing. Otherwise, you're going to get very confusing solutions. Move on to your setup. If you know how many processors your computer has, you can up this. I think ANSYS student is limited to 4, so I'm just gonna do 4. Always do double precision because accuracy. And start. Let's go move on to our setup and solution. Now here's where we could start checking off sections to what we are expected to find. But first, before we do that, we need to set up our simulation so that it has all of the prerequisites that are being asked for. Of course, you just are at the mercy of Fluent and how long it takes to load along with your computer. Beautiful. You can see that ANSYS already recognizes my inlet and my outlet, so no issues there. Start off on your model. The instructions say that we are running a laminar, viscous laminar 2D steady flow. So there's laminar, which is a form of viscous. No energy, no multi-phase, no radiation, no heat exchanger, no species, ignore discrete phase, ignore, 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 and ignore. That's all you need to do in models. It's simple. Let's move on to our fluid, our air. So we are running air. And here in the instructions, he says that density is 1.2. Additionally, he says that the viscosity is going to be simplified to 1.8. This just makes calculations easier. And it's not changing the numbers too much. It's a pretty small estimation anyways. But change create, change create, change to create again, because I don't trust Fluent. That's good. No changes to solids. You're probably not going to touch that. Cell zones, you don't have to touch. Boundary conditions. Let's just make sure everything is working. ANSYS is pretty good, and it should recognize everything, but it does recognize our inlet, and since we're here, let's adjust. Our free stream velocity is 2 meters a second. Awesome. Apply that again, because you're not so sure. Internal, there's an internal outlet. Pop open this. It is a pressure outlet, so there should be no changes. It's just pressure to 0, and the movement of pressure is going to cause velocity to go. Astonishing stuff. Close out on that. Excuse me. Symmetry. This is what I was talking about earlier with that top wall. See, we have a symmetry. That is our top wall. If you don't have symmetry, if you didn't name it symmetry, it's going to appear in here, whatever you name it, and you need to rename it, or you need to re-ID it as a symmetry. I believe you could just name the zone here and it'll fix. But whatever. Moving on. No mesh interfaces, no auxiliary digit. Ignore. Ignore this, I think, for now. And let's move on to methods. I'm going to keep it encoupled. You can run simple. It doesn't change that much. Simple runs faster, but I think it's a little less accurate. Whatever. Moving on, let's go to our residuals. Let's increase our accuracy by upping those residuals by 2 more. You can go as high as you want, or low as you want technically, but just know it's going to take longer, but you are going to be more accurate. Actually, because this is boundary condition, I'm probably going to make these really low. Very tiny residuals. Nor move on to your initialization. Do a standard hybrid. Doesn't really change that much. Here, X velocity. 2 meters a second. It's exactly what it says on our instructions. There's our inlet. Awesome. So compute from inlet to initialize, wait till it stops loading, and you know it works when this disappears and this changes over here. Move on to run calculations. Set your number of iterations up to whatever your heart desires. It shouldn't reach past 1,000. If it does, something is wrong. And you could spend hours trying to figure out what is wrong, but it probably won't work, so you might just want to cut your losses and restart your geometry. I struggled with part 3 on that. Moving on. So once you have all that, just calculate. It's going to take a while. The more chords you give it, the faster it'll go, along with if you're running it on simple, but lightning quick, because the simulation was right and there was no issues. And we even went down to 7 on our residuals. So now that you have that, we can start with the first part. So the first part asks for velocity with vectors and pressure contours around the flat plate. And because it asks for vectors, we're actually going to exit out of solution. Just because I think the contours and the vectors look much nicer in the results section, the results app of Fluent. So just pop open results. Move on over to the z-axis. And we're going to get our velocity contour. So name it what you want. I'm just going to name it something simple. Velocity contour. The location. So it is asking for the velocity contours around the flat plate. However, don't put that here. You're going to put symmetry 1 because you want to see the velocity contours of this. There's going to be no velocity contours in the flat plate. The velocity contours are in the fluid, not in the plate. So your location is going to be the symmetry. If you do it on the plate, you're going to just see velocity decrease as, well, you're actually not going to see any velocity at all because this is a laminar flow. So there's a boundary layer in the no slip condition. Moving on. Select velocity in the symmetry 1. Set a number of contours that your heart desires. I'm going to do 150. More slower, but more accurate, but it can also overclutter your screen. Apply it so we can get a look, and look at that, a bright block of red. But what do we see down here? If you look at that, there's a rainbow. This is the rainbow of success because you got what you're supposed to be getting. You can see here, look how tiny this boundary layer is. Right here at the bottom, 0. No slip condition along the plate, but up here's velocity, and there's an increase in the velocity. And if you would notice, this actually increases as you go along the plate, but it kind of flattens out after a while because that's just how fluids work. Moving on. If you want to make this look nice, to take screenshots, For your project report, I recommend going into the legend view, and you can. I personally like to do is go horizontal, like that, and then you can down the precision, not that big because it's just this graph. Who really cares that much? Put it into fixed because the E is too much to look at. And wow, look at that. That is a beautiful graph if I've ever seen one. I'll move it over here, screenshot that. That's gonna be your boundary layer right there. I mean, you probably don't even need all this up here. You can probably just zoom in on the bottom and screenshot that. Moving on. So now that we have our velocity contour, if you want to show the contour and the vectors, first let's drop the transparency of our contours, not to 1, to 0.60. So 60% transparency, and you can actually see the contours now. But let's add some vectors. You'll never guess what I named this. Velocity vector, that's right. Location, symmetry 1 again. Sampling, vertex. This is going to take a lot of trial and error. Okay, awesome. I like arrow 2D, I believe. But first thing you're going to do is apply. That looks disgusting. Let's drop that symbol size by half. That looks a little bit more legible, but still pretty illegible. Up the factor. 3, illegible. What about 5? Now we're getting somewhere. How does 8 feel? That looks much better. But let's go all the way to 10. Would you look at that? Can you just see that perfect boundary layer develop? Look at this velocity vectors, or vector velocity profiles. You can literally see it within the vectors. This is beauty. I mean, it gets a little confusing down here, but if you wanted to, drop this down, 0.2. Go. Maybe arrowhead. How's arrowhead look? That's perfect. Now you can actually see your velocity profiles. So that right there, screenshot. Maybe not from here, whatever. But moving on. Now you need to get the velocity profile. I believe that could be done. Let me see if that could be done in here. I'm going to start a chart for velocity profile where the x-axis. Oh, wait. We need to do it at 2 different locations. Give me a sec. Velocity y. Okay, we can come back here. Give me a sec. First, I got a little ahead of myself. Let's go back to 3D view so we can see what we're looking at. Now, I'm going to turn off our velocity contours and our velocity vectors. So we're just seeing our box. Location, line. So this is going to be, let's say 30, can't do numbers. So let's do first, let's just call it developing region. I don't know. Name it whatever you want. You just can't name it 35 centimeters, unfortunately. So it's going to make a line between 2 different points. Point 1 is going to be at the bottom, because I say so. So on our x-axis, it's going to be 35 centimeters. This is being measured in meters. So put a dot right there at the bottom. Now, same exact point, 35 centimeters. However, this is going to be 1 meter tall because our box, or wait, this is a percentage, sorry. So this is 35%, and 35% of 100 centimeters is, you guess it, 35. And this is going to be 100 because 1%. Yeah. I'll do, I don't know, 150 samples is what I'm feeling today. I'm going to make my color bright green so I can see it. And then up the line width so I can also see it. My eyes aren't like what they used to be. Boom. That's not right. Give me a second. Maybe it is 0. It is. Technical difficulties. Give me a second. Ah, it's 0.5. I forgot this is not percentages. These are actual measurements. So this is 0.5, or this is 5 centimeters. 50 centimeters. This is measured in meters. Apologies. So that's your first line. Now we need a second line because it asks for 2 lines. So I'm just going to call this developed region. Same thing. 0.75. 0.75, and this, if I don't make the mistake again, is 0.5. I'm going to make this a different color because I feel like it. So it's going to be 2 with a line with a 4. It's going to be blue. Look at that. So now that you have your 2 lines, let's get our data for velocity profiles. So velocity profile, we can put them both in one. So it's just called velocity profiles. Here's your title, velocity profiles. Boom. And here we actually need to add 2 data series. We're gonna name the first one the 35 centimeters. And the second one is going to be, you guessed it, 75 centimeters. At 35 centimeters, the location is going to be in the developing region, whereas 75 is going to be up in the developed region. Check that they're both right. Move on. Our x-axis is going to be velocity, because that is how velocity distribution graphs work. So velocity on the bottom. You'll see it once we make it. Velocity. And then y is going to be the height from the plate. Apply it. Wow. That doesn't exactly look at what we're expecting to see. And you would be right, because it's extremely zoomed out. This is the entire height of the box. We don't want to see all that. So we're not going to determine ranges automatically. There's no such thing as negative height on our box. It's going to be minimum 0. And the maximum is, I don't know, let's start with 0.1. Apply it again, and you could see it looks a little bit more different. Try it again. Let's go down to 0. I don't know, 0.2. Apply, and you can actually see the developing region right here. You can make some other adjustments to your graph. Make it scatter if you really felt like it. You probably don't want to. So let's do XY. I think there's actually an issue with our developing region line. It's the number of samples. There we go. Okay, that was my fault. So now you can see, you upgrade the samples. And if you actually up the samples even more, which I'm going to do, so we can get really accurate lines, you'll see how much they curve. There you go. You can actually see the velocity profile. This is what you would expect, because as it goes farther on the plate, the velocity profile develops more, which means it actually gets slower at the bottom because the boundary layer gets thicker. So you can see on velocities at the bottom, 75 is actually slower at higher points. That's because that boundary is getting thicker. So those are your two velocity profiles. You can compare it with Blasius's. It's going to look a lot like the blue one, especially if we go to our graph here and we reduce our y-axis even more down to, I think, 0.1 is when it looks really good. Yes, this is very similar to what Blasius's is going to look like. It looks very similar to that, which is the expected. Blasius isn't perfect, but is a very good estimation of viscous laminar 2D flow. Moving on. The wall shear stress and skin friction. I do not believe those can be calculated within the results. But let me check real quick. Do X along the length, and I stand corrected. You can calculate wall shear. Okay, so your series is going to be wall shear stress, its location, stress and skin friction coefficient along the flat plate. Let's make one more location for this one. Apologies. Flat plate. 0.0000, and it's going to be at the very end. If you remember, our plate is 1 centimeter, or 100 centimeters, which is 1 meter. Let's look at that. So, it was already correct to begin with. Samples. I'm going to up that number to something high so we can get accurate data. Flat plate. Now, remake that chart. Wall shear stress. Wall shear stress over plate. XY. Wall shear stress. Location is going to be over flat plate. The x-axis is, as you would guess, x over the plate. Oh wait, not wall shear, x. And then y is going to be wall shear. Apply it. That is exactly what you'd expect. There's high force at the beginning because the boundary is not fully developed and there is the velocity is actually acting on the plate because there's not a large boundary layer to block that speed or to block the velocity from affecting it. Similarly, now we're going to get skin friction. So skin friction coefficient along plate. Data series is going to be skin friction coefficient. Location, again, flat plate. X-axis is going to be X. Y-axis is going to be... Uh-oh. You cannot find it in results. So, close out. Go back to solution. I don't know why, but not all of the values in solution can be plotted in results. I believe results is like a newer section of ANSYS Fluent. Okay, here we're going to make an XY plot. It's going to be named skin friction coefficient. Your y-axis is going to be not properties, wall fluxes. Oh, yep. Skin friction coefficient. See? Not everything in solution can be found in results for reasons that I don't know. Regardless, your surface flat plate bottom, this is fine. If you want to get the data, click this. It's going to change, and then you can write the data to a file. You can find the file where your project is saved. Then you can open that in either text or Excel, but do note that the x-axis and the y-axis are like shifted or something like that. I don't know how to say it. You could just highlight both the columns in one highlight, and then in Excel, just filter from smallest to largest. It won't mix up your X and Y's. They stay together. I don't know why. That's just how ANSYS saves files. Regardless, moving on. You could plot this, and you could see skin friction coefficient acts as you would expect. It's because skin friction coefficient and wall shear stress are directly related to each other. To get skin friction coefficient, wall shear stress is in the equation. It's at the top. So, because they're both positively related, as the skin friction, or as the shear stress decreases, so is skin friction coefficient. So that's why they have the same looking graph. And let's see if we can get drag coefficient. I don't trust. Let me print this. This does not get what I want. Okay, if I'm not mistaken, you should be able to go into report definitions, make a new report. Should be drag report for drag coefficient along the flat plate bottom. Let's print that to console. Compute. There you go. That would be your drag friction coefficient that ANSYS gets. You could just solve yours out as well because you need to get them both, but that is everything you need to do for part 2 of Project 1. Thank you very much.